So we ask ourselves, can we actually oscillate the inductor very small amount to stabilize the system?
And you can.
And we did it.
That's amazing.
Wow. Recently, by the way, literally in the past few months, I became very interested in a very different field. I became interested in Kapitza's inverted pendulum.
Okay.
Do you know what that is? Well, you all know, obviously, the simple pendulum. When you do it like this is stable. You know that if you actually bring the pendulum here, it's unstable, obviously. Back in early part of 20th century, in 1908, I think, there was recognition that if you actually have this pendulum over here and you move the base of it up and down very rapidly, but very small amount, this pendulum actually became stable back there. This was observed, but nobody knew. I could not actually mathematically evaluate why that is the case until Pierre Kapitza in 1951 mathematically solved the problem very elegantly. I loved it, by the way. Again, recently I became aware of this topic. So I went back with one of my postdocs. We looked at this. He did a beautiful job, by the way, in actually mechanical structures to do that. And he showed very nicely that if you actually have a very small displacement of the base of this pendulum, but with a very rapid frequency, and there's a condition that frequency should be greater than something, this pendulum becomes actually stable. Now, it's interesting, by the way, that problem actually started a new field of vibrational mechanics.
Oh, right.
So there's a lot of interesting mechanical problems in which if you actually vibrate or modulate certain part of the mechanical system, the stability of the system will change. Even though the variation is very small, but it can actually affect the stability of the whole system. And in fact, there is a whole area that I'm reading about it. I call it vibrational resonance. So just out of curiosity, I said, can we bring this into electromagnetics? So we decided to actually look at this problem, just a simple LC circuit. If you look at an LNC circuit, that's also an oscillator. The formulation is identical with the pendulum, mathematically. It's basically a second order differential equation with a periodic solution. How do we make LC unstable? By actually making the C negative. And there's a whole area in electronics known as non-Foster circuit elements, which C is negative. It has to have a gain medium. In other words, you have to have a transistor to do that. If you make C negative, of course, this system becomes unstable and you have an exponential increase of the current. So we ask ourselves, can we actually oscillate the inductor very small amount to stabilize the system?
And you can.
And we did it.
That's amazing.
Wow. We did it. Now we are trying to actually bring that into wave propagation. So could we actually make some of the unstable scenarios in optics stable by just slight variation? So we're calling it vibrational electromagnetics.
Oh, that's very interesting. I also wonder if that translates then to quantum harmonic oscillators.
Maybe, exactly,
where you can have these small
yes,
fluctuations.
that's right. So
in the optics case, what would you be oscillating?
Exactly. We don't know that yet, but we are thinking maybe just index of refraction. Very small, maybe. Again, we have to look for a scenario that is unstable and we want to make it stable. And of course, that could be also in nonlinear system. So we don't know that. We're at the beginning of this field. At least we did it for the circuits, and we saw what would happen if you change the inductor. Now we are actually working it on one-dimensional wave propagation. So if I have a transmission line and I change the L with C, what would happen? Eventually, we would like to make it for the wave propagation and in optics. We'll see how it goes. But that's another example that just a curiosity. I just became fascinated by this because I have a very interesting collaboration with a colleague, Emmanuel Fort, in Paris, that he is doing great work on water waves. We are part of a team that we study time-varying metamaterial. So that's another area that we are working in my group. We call it four-dimensional metamaterial. These are the material that you actually change the permittivity in time. Anyway, Emmanuel Fort and Matthias Fink in Paris, they've done a beautiful job on water wave. So they have a water wave and they change this and they see how the time reversal works and so on and so forth. Emmanuel Fort has done this beautiful work of, again, inspired by Kapitza's, that he takes this tank of water and he turns it around. So obviously the tank of water, he turns it around, the water has to come down. But then he starts vibrating this. and the water actually stays. Very interesting. It's completely identical.
Can we see it in the video?
Yeah, oh yeah, he has it. He has it. I will ask him to send it to you. Yeah. And so I became very fascinated by Kapitza's work. And I said, okay, very good. Emmanuel has done it for a water wave. Can we do it with electronics? Okay.
You're turning the world upside down.
Anyway, so
defying gravity.
It is interesting. This always fascinates me, to connect from one field to the other, to learn something new. It makes it exciting.